Hello, my name is Kumar Saurav and I am a research scholar in the School of Technology and Computer Science at TI for Mumbai. Today I am presenting the paper titled Game of Ages, which is joint work with Rahul Vase, who is a faculty in the same school. To start with, let's consider the example of a smart home network which consists of multiple smart devices interfaced to a common server. This can be represented as follows, consisting of multiple sensor nodes which senses data from the environment and communicates it to the server, which in turn controls actuator devices, typically based on the data obtained from the sensor nodes. In this particular talk, we are interested only in the first part of the network, which consists of multiple sensor nodes and a common server. So note that these sensor nodes typically want to communicate the data as soon as possible to the server, because fresh data is of much greater value as it helps in taking timely decisions, for example, in which is critical in many IoT applications, including real-time control. So in context of data freshness, it is imperative to talk about age of information, which is a metric for data freshness. To understand this, consider the example of a system consisting of a single node and a server. Assume slotted time model and let the transmission delay is 0. Now this node, sensor node, which we in short we shall just call as a node, this node S wants the server to be updated about its status. So the node wants to achieve this by transmitting its packet, by generating data packets consisting the information about its status, and it wants to send this information to server by transmitting this packet uh, periodically. Now to start with, let's consider the server knows the status of node at in the 0th time slot. So in first time slot, the node transmits data packet, however that is not received by the server. So now the last node status is 1 time slot old. In time slot 2 also a packet is not received by the server. So now the last known status is 2 time slots old. In time slot 3 again it becomes 3 time slots, or the last known status becomes 3 time slots old. However, in time slot 4 a packet is transmitted by the node and is also received by the server. So the last known status is now 0 time slots old. And now again in fifth time slot the last known status becomes 1 time slot old because no new data packet is received by the server. So this last known status becomes old and old until a new packet is received by the server consisting of the status information. So this quantity that we have plotted here, this is basically called age of information, which is mathematically given as follows. So for a node L at any time I, its age is equal to I minus mu Li, where mu Li is the generation time of the uh, most recent packet of node L, which has been received by the server up to time I. So this plot gives a more general plot of age against time. That is, it makes no assumption on transmission delay, etc. So now, uh, coming back to the network of interest, so such networks have several constraints with them. So, for example, nodes are oblivious to each other. Now, consider this example of a smart home network which consists of multiple nodes. Uh, but these nodes need not know about each other. So they can't communicate, and hence the sharing of the channel causes interference. Um, Also, transmission is costly. So most of these smart devices are either battery powered or they harvest energy from environment. In either case, they have constraints on their energy usage, and because transmission requires more energy, uh, there is a cost associated with every transmission. Now, going ahead, let's fix the system model. So we will, throughout this presentation, we will consider a system consisting of n nodes and a single server, and time is discretized into slots, and nodes generate packet in every slot. So, and for any node L, its age in slot I will be denoted by delta Li, and cost per transmission is CL for LS node. And note that this cost per transmission can be different for different nodes. Also, simultaneous transmission from multiple nodes result in collision, and nodes are oblivious of each other, so they don't know about each other and about each other's transmission policy or even the existence of other nodes in the network. So the only thing that a node gets to know from the network is that when it transmits a packet, it only gets to know if its own transmitted packet was received by the server or not. Now for this system, the objective is to obtain a stable transmission strategy for each node that strikes balance between average age and average transmission cost. With the term stable here, we mean to say that the system should be able to work in equilibrium. That is, neither the average transmission cost nor the average age grows unboundedly for any of the node. Also, the strategy should work in under decentralized topology, and it should not insist for explicit network information because it may not be known. Now, the challenges in solving such a problem is so low average age requires frequent transmission. However, that will incur large transmission cost. So even if we have only one node, this uh, transmission decision is not trivial. Uh, However, we have multiple nodes and nodes cannot coordinate due to decentralized topology. So there will be interference, and because of interference, all the transmitting nodes will incur transmission cost without any reduction in age. Also, a typical approach in solving such problems is to model this scenario as a game and to analyze its Nash equilibrium, to analyze how the nodes behave at Nash equilibrium. However, in this particular case, it is difficult to model uh, 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 a non-cooperative game because for that we need a utility function. However, because of interference, utility function of each node will depend on other nodes. But because the nodes don't know about each other, so utility function cannot be written for a node that can be computed by a node. So there is no such obvious utility function, and hence a game cannot be defined uh, for practical cases. Uh, so to solve this, we have proposed a learning algorithm. Uh, Now, before going into the algorithm, so we have we consider a slotted time model. Now we define a frame. So let m be any natural number. So we define a frame as like a group of m consecutive slots. So slot number 1 to slot number m, these form frame 1. Slot number m plus 1 to slot 2m, that is frame 2, and so on. Now to start with, we initialize transmission probability for each node to, before frame 1 starts. So for node L, we initialize the transmission probability as PL1. Now the node L transmits the packet generated in each slot with probability PL1 in frame 1, and at the end of frame 1, we compute the average transmission cost and average age incurred during the frame 1, and we use the given expression to calculate the transmission probability for frame 2. And again in frame 2, we transmit the packet generated in each slot with this computed transmission probability PL2, and again we repeat this step, that is we compute the average transmission cost and average age at the end of frame 2 and calculate the transmission probability for the next frame, and so on. Now coming to this expression for computing the transmission probability, tau t here is the learning rate, which lies between 0 and 1, and the transmission probability for next frame, that is PLT plus 1, is a convex combination of PLT and this second term that is within the brackets. Note that this second term here again consists of two terms. Here the first term is a decreasing function in average transmission cost incurred during TH frame. So if average transmission cost is large during TH frame, so the value of this term will be smaller, and this suggests that PLT plus 1 will be smaller, and hence the node should transmit less frequently in T plus 1th frame. So if average transmission cost is large, that means the node is transmitting very frequently in TS frame. So this suggests that the node should transmit less frequently in T plus 1th frame. So PLT plus 1 will be smaller. However, because of this negative sign, this second term here is an increasing function in average age. So if average age in TH frame is large, this will cause PLT plus 1 to be large, and hence this suggests that the node should transmit more frequently in next frame because average age is large. In this way, these two terms take care of the trade-off between average transmission cost and average age. Now note that we call this a learning algorithm because this algorithm learns the transmission probability from the information from previous frame, that is transmission probability in previous frame, that is PLT, and the average transmission cost and average age incurred during previous frame. Also note that this expression does not need to know anything about other nodes or anything else from the other nodes or its their transmission probability, transmission strategies, etc. That is why this is completely local. Local in the sense it can be implemented by a node without knowing about uh, other nodes in the system. Now coming to the main result, so if all the nodes obtain their transmission probability using the learning algorithm that we just proposed, then their transmission probabilities converge to a unique fixed point with probability 1. Uh, so here the unique fixed point, this is all this unique this fixed point is unique, and it is also non-trivial. So it takes care of the number of nodes in the system and their transmission cost. Also we show that this unique fixed point is actually a Nash equilibrium of a non-cooperative game, which is as follows. So consider this non-cooperative game G, where n nodes act as players and each node chooses an action PL, that is transmission probability, from the set of valid transmission probabilities, uh, and the utility function is given as follows. So a few slides ago we discussed that we can't define a game because the utility function is not obvious. So just to so note that this utility function is not the actual utility function that can be used in practice, because as we discussed earlier, we can't write a utility function that is known to a node because the utility function will require the information from other nodes. So this utility function also, this requires the knowledge of CL that is known to a node L. However, this also requires the knowledge of BL, that is the transmission probability that no other nodes transmit in that in a frame of the TH slot. So this will require knowledge of other nodes. This requires so this is not known to a to node L. So UL is a utility of node L, but node L cannot compute this utility in practice because it doesn't know the transmission probability of other nodes. So BL is unknown. So in practice, such a utility function cannot be defined. I mean, it cannot be implemented in practice. That is why we call this as a virtual utility function. And hence, this non-cooperative game is only for analysis purpose, and it cannot be implemented in practice. So how we got this utility function? So note that this is the learning algorithm that we defined. So this is exactly same as the previous expression. It's just that we have just rearranged one term here. This PLT moves from here to here inside this bracket. Now, in expectation, this expression is equals to this, where we have defined BLT as probability that no other node transmits. And we note that this looks similar to a gradient ascent algorithm. So in expectation, this learning algorithm is maximizing some utility, and hence we assume that there is some utility that is being maximized, and hence we equate the gradient of this utility with the term here, the second term in this expression. And hence integrating on both sides, we get this utility function. Now coming back to the main result, so we prove it as follows. So we show that the learning algorithm converges to the best response strategy of the game that we just mentioned. And for this we use the convergence result discussed in the book mentioned in the footnote. And then we show that the best response strategy of the game converges to the unique Nash equilibrium of the game. For this we use a contraction mapping theorem. So in the process we also get to know that the game has a unique Nash equilibrium. Now to compute the efficiency of the, to analyze the efficiency of the learning algorithm, we analyze the price of anarchy. So utility, for this we define the utility of the system as the sum of utility of each node, and price of anarchy is given as the ratio of utility of the system when nodes are transmitting with optimal probability divided by the utility of the system when the nodes are on the at the worst Nash equilibrium. However, in our case, we only have a unique Nash equilibrium. So the theorem for in context of price of anarchy is that if each node follows the proposed learning algorithm, then price of anarchy for the game G approaches unity if number of nodes is large. To show this, we use the property of utility of the system, and then we show that with when number of nodes is 1, this price of anarchy is 1, and when number of nodes increases, this price of anarchy increases. I mean, it goes far. This PNE goes away from POPT. However, when number of nodes increases further, this PNE again starts to converge towards POPT. So that is why as number of nodes become larger, this PNE approaches POPT, and hence POA converges towards 1. So note that price of anarchy close to 1 tells us that this algorithm is efficient. So, and this property was actually also observed during the numerical simulations that we carried out for our learning algorithm. Then we observed that our learning algorithm also converges very fast. So we put it under test when number of nodes changes in between. So to start with, we simulated the system and we started it with certain number of nodes, and we changed the equilibrium at t equals to 20 by changing number of nodes, and then we restored the equilibrium again at t equals to 80 by restoring the number of nodes. So we observed that the transmission, this learning algorithm the transmission probability obtained using this learning algorithm converged very quickly to the equilibrium, and when the equilibrium was changed, it followed the newer equilibrium. However, one can argue that this convergence was slower for the newer equilibrium. That is because we had defined this learning rate tau t in our learning algorithm, which is a decreasing function in time. When time becomes large, this learning rate becomes small, and hence the convergence is slower. However, this problem can be solved by resetting the time whenever it becomes very large. To summarize, we proposed a learning algorithm that guides a node to equilibrium when nodes wish to lower their average age and average transmission cost. And we identified the fixed point as Nash equilibrium of a non-cooperative game, and we quantified the efficiency of the learning algorithm using price of anarchy. And we showed that it converges to 1 when number of nodes become large. Also through simulation, we showed that the convergence is fast and it is robust against disturbance in number of nodes. Thank you.